alpha delta Sasaki manifolds and strongly positive curvature.
Thank you very much. Thank you to all the organizers to inviting me to this nice place. And yeah, what I would like to add are two small comments. One is, it's a discussion we had yesterday already at lunch, that I'm really impressed how large the impact of the Simons Foundations is on mathematics and pure mathematics in particular as a whole, and how lucky we are to have such funding available for doing what we love to do, but where sometimes lack of funding poses a serious issue. So this is really a huge benefit for us. And the second thing I would like to mention, that's something probably you don't know, but Marburg, the university where I am, it's a capital of the blind people in Germany, because it hosts the only boarding school for blind pupils in the German-speaking area where they can get a high school degree. And so we get a lot of blind students at our university. And in fact, in case you're interested in these things, I'm leading a large project about how to make math accessible for blind students. It's not obvious at all because of all the non-textual information. And I'm so impressed by how most buildings, the streets and everything here in Brazil is ready, right, to make life just easier for blind participants. This is really amazing. So that's something I notice immediately whenever I go somewhere, because it's not obvious at all, and I guess that's a model to follow. Okay, so that's my personal statement, and now I would like to talk to you about this class of 3 alpha delta Sasaki manifolds and a range of applications, namely the notions and geometry related to issues of strongly positive curvature, which I'm going to explain, of course. And whatever I'm going to present is joint work with Julia Di Leo from the University of Bari and Leander Stecker, my former PhD student, who is now actually learning first words of Portuguese because he's in Lisbon for a while, right? And so we have this series of 3 papers, and whenever I'm not mentioning where a result comes from, then you can assume it's in one of these. Okay. So let's start with a very general context, namely curvature operators. Okay, so we start with a Riemannian manifold. Analogy is just a Levi-Civita connection. And of course, we have the Riemann curvature tensor, and we can interpret it as a symmetric map on 2 forms, right? Just defined in the usual way. And I like to have a minus sign over here. Okay. And there are 2 things you can ask when the symmetric operator on 2 forms is a positive operator, right? And there's another notion which we are familiar with of positive curvature, namely positive sectional curvature. And we know that positive curvature operator implies positive sectional curvature. And in a certain sense, I would like to follow the idea that on one side, this side of the equation, namely having positive curvature operator, is something which is extremely well understood because of the result of Böhm and Wilking, which states that whenever this is the case, your manifold is actually a space form. Right? So there's not much more to say. On the other side, understanding positive sectional curvature, as we know, is challenging. Okay. And the notion of strongly positive curvature basically sits in between. So in order to formulate it properly, let's look at the Bianchi map, right, from symmetric operators on 2 forms to 4 forms, which is just that. And we know that the Riemann curvature tensor is, of course, in the kernel of the Bianchi map, which is just what we typically call the space of algebraic curvature tensors, meaning all tensors having all symmetry properties that you would require from a tensor to be the curvature of a Riemannian metric, right? Okay, so therefore we have the splitting in kernel and image. And now if you look at that, there is a crucial observation due to Thorpe in the 70s, namely, whenever you have a symmetric map on 2 tensors, right, and on 2 forms, sorry, then at least formally, we can define kind of a sectional curvature for it by just taking the usual formula. And if your element omega happens to be actually a four-form, right, which is, of course, something any four-form can be interpreted as a symmetric map on two forms, from two forms to two forms. So if it is actually a four-form, then it does not contribute, meaning that the sectional curvature of the Riemann curvature tensor plus a four-form is just the same as the sectional curvature of the curvature operator itself, right? So this led to the following notion, namely a Riemannian manifold is said to have strongly positive or respectively non-negative curvature if there exists a four-form omega such that R plus omega is positive as an operator or respectively non-negative. So this is the notion we would like to follow. And then it is easy to check that this notion sits inside or in between positive curvature operator and positive sectional curvature. So since we have this beautiful blackboard, let's use it. Okay, so positive, respectively non-negative, strongly positive, non-negative curvature, right, means there exists a four-form such that RG plus omega is positive or non-negative. Okay, and obviously all the other induced notions from there. Good. In dimension 4, these two notions actually turn to be equivalent. So strongly positive curvature is actually exactly the same as positive sectional curvature, which is already to be found in the work of Thorpe. If one investigates or if one looks up the nice work of Püttmann from the late 90s, then one finds a few homogeneous examples, namely among the compact rank 1 symmetric spaces, spheres, complex projective spaces, and hyperbolic and quaternionic projective spaces, but not the Cayley plane. Okay. In dimension 6, we have SU3 over 2, so this is, of course, a nearly Kähler manifold as we know it. Then we have the Alov-Wheeler space, read 1, SU3 over S1, and another 7-dimensional space, SO5 over SO3. Right? The progress on this notion of strongly, or the interest on the notion on strongly positive curvature, basically started again by some very nice work by Betziol and Mendez from 2015 and 2018. Namely, so first thing is that they looked at the other Wallach spaces, right, W6 being the first of them. So W12 and W24, SP3 over SP1 cubed and F4 over spin 8, together with the more general Alov-Wallach spaces in dimension 7 and the Berger sphere in dimension 13, these are all homogeneous spaces with strongly positive curvature. Okay? Okay, so in particular, their proof implies also that the Cayley plane does not admit a homogeneous metric with strongly positive curvature. They prove that strongly positive curvature behaves very nicely under submersions. So having one, and if my large space has strongly positive curvature, then the small one has strongly positive curvature as well. Right? And they prove what they call the strong Wallach theorem for homogeneous vibrations, because basically the examples above here, the Wallach manifolds, all fit into a nice vibration, H in K in G, right? So that KH fibers over, no, GK fibers over GH fibers over KH. And then we can play the game between these sub-algebras to investigate the curvature properties. Okay, So that's what they have. And now, how did we start, or why did we get interested in looking at manifolds with strongly positive curvature? So it all relies on this 4-form omega. The question we asked ourselves is, if all the manifolds which are listed on the slide, on the previous slide, right, all of Wallach, nearly Kähler, etc., all these manifolds carry special geometric structures. So if this is a good concept, it should be possible to understand the 4-form through the geometric structure existing on these manifolds. And our goal was to relate these two notions, right? To see whether we can understand the 4-form from the geometry. So, where does omega come from, right? I should add that the proofs by Betziol-Mendez are not constructive. They show the existence of a 4-form, but they don't say what it is. Okay, so we wanted to pinpoint it. Okay, so, well, easy examples. For example, complex projective space, you can just take the complex structure and wedge it with itself, and then this does the job. So that's certainly a good candidate. Okay. Whenever we are in the situation of a homogeneous vibration, such that the base GK is actually a compact rank round symmetric space other than the Cayley plane, then what they at least were able to show is that, so if I call M the tangent space of GK, P the tangent space of KH, right, then the tangent space of the manifold I'm interested in, M here in the middle, G over H, is M plus P. And they could argue that the 4-form is not arbitrary. It doesn't mix any components of M and P just in any arbitrary way, but actually it has only two kind of summons in lambda 2 of M and times lambda 2 of P and the 4 forms on M. So this gives already a first hint how it is encoded in the geometry of the manifold. Okay, next step, we look at the nearly Kähler SU3 over T2 and see that actually the gray connection, right, which is a metric connection with skew torsion, which is actually parallel, right? Turns out that omega equals dt does the job where t is exactly the torsion of the connection. So this gives us a hint, and actually that's the naive idea we would like to follow. And similarly, on all of Wallach manifolds, we know that they have G2 structures and 3 alpha Sasaki structures, and so we would like to see whether the G2 structure or the 3 alpha Sasaki structure can help us in identifying the 4-form omega. Good. Now, where do these 3 alpha delta Sasaki manifolds, which appear in the title, enter the game? Okay. So we know that the only 3 Sasaki metrics with positive sectional curvature are the standard metrics on spheres of dimension 4n plus 3. And joining results of Derricott and Eschenburg, actually this means that there exist 7-dimensional 3 alpha delta Sasaki manifolds with positive sectional curvature. I still didn't say what they are, but at least we can interpret their results as claiming this. So we know that if we are looking at the class of 3 alpha delta Sasaki manifolds, we know that they do admit metrics with strongly positive curvature, and therefore asking what is the 4-form is not an empty problem. Good. So what I would like to do from now on is, so first, I'm going to describe very briefly this new class of 3 contact manifolds. I'm going to say what its canonical connection is, which is going to be a metric connection with skew torsion that is indeed parallel, just as in the nearly Kähler case. We shall explain shortly that they do admit a canonical submersion over a quaternionic Kähler or hyperkähler manifold. So that gives us a good idea about the geometry of these spaces. And then Well, one of the advantages of this class of manifolds is that you can do a lot of curvature computations very explicitly. Okay? So basically, we know all components of the curvature tensor. Of course, they might be complicated. They depend on the geometry, but we have them. And using this information, right, we can actually say something reasonable. And so use all this information about the curvature to apply it to the problem of strongly positive curvature. And in particular, I would call it quantitative strongly positive curvature. In a sense, what is omega, right? And what can we learn about the geometry and the curvature properties by doing so? Okay, so let's start. Well, almost three-contact metric manifolds. One of the disadvantages of doing contact geometry is that you get these very long, almost contact para-Sasaki, nearly something, these long sentences, which at the beginning don't feel intuitive. So let's try to circumvent that. I would like to look at a manifold of dimension 4n plus 3, has a Riemannian metric G, and three almost contact structures, eta, psi, phi, right, labeled with indices 1, 2, 3. And except that each one defines an almost contact structure on the manifold, right, which in particular means the psi i's are going to be the wave vector fields, eta I are the dual one forms, and the phi i's are an almost complex structure on the orthogonal distribution to the wave vector fields, right? We have the following situation in the vertical space, which is, by definition, anything spanned by the free Reeb vector fields. So the free Reeb vector fields are orthogonal to each other, oriented in a positive way, and we have these almost complex structures on the orthogonal subspaces of the tangent space. So if I restrict my attention to the vertical space, in particular, the orthogonal space of a Reeb vector field has a two-dimensional component which lies in the vertical space. Right? So for example, if I take psi1 here, which is this vector in blue, okay, then the orthogonal space has this two-dimensional plane in the vertical space here. And we have an induced orientation, right, by the action of phi. And basically, phi should be such that now psi2, psi3 lie in this orthogonal plane, the two other wave vector fields, and it maps xi2 to xi3, and so on, just following these orientations in a suitable way. So the orientations, how to map vector fields to each other, are indicated by the arrows on the edges of the plane. Okay, so these are the compatibility conditions, which I call what down here, psi1 times psi2 is psi3 on V with the cross product. Right, phi1 composed with phi2 is phi3 on the horizontal space, which you can't see here because I'm only depicting the three-dimensional vertical space. And phi1 maps psi2 to psi3 plus any cyclic permutations coming from these conditions. Right, and obviously the horizontal space is the orthogonal complement of the vertical space, which you can just describe as the intersection of the kernels of the three dual one forms. Okay, the structure group then, by the way, is reducible to SPn times unit in this three-dimensional vertical space. Good. So this is the world of almost free contact manifolds. And moreover, just as vanishing Neuenhaus tensor is a measure for integrability on almost complex manifolds, there is an analog on contact manifolds, namely the vanishing, well, of the Neuenhaus tensor of this almost complex structure, which basically says that you get an integrable structure one dimension higher. Not so important. The name is slightly different because we call this a hypernormal structure. Okay, so if all three analogs of the Neuenhaus tensor vanish, and here are some remarkable classes of free almost contact manifolds. There are free alpha Sasaki manifolds, which means that each of these single almost contact structures is alpha Sasaki. Free Sasaki means just that the alpha in alpha Sasaki is 1. Free cosymplectic if all three are cosymplectic, free quasi-Sasaki, and if all three structures are quasi-Sasaki. Now observe that it's a known theorem that any free alpha Sasaki manifold is actually Einstein. Okay? And the second observation here is that all these definitions are basically of the type, we call it X if all three almost contact structures, if I view them in an isolated way, have the property X. So I'm not asking for any compatibility conditions between the three almost contact structures, or I'm not asking, well, how do they see each other, right? And this is what free alpha delta Sasaki changes. There's a relation between the three almost contact structures. Okay, a classical theorem of Kashiwara is that if these are actually contact manifolds, so if a free almost contact manifold satisfies d eta I equals 2 alpha phi for all three almost contact structures, then the manifold is automatically hypernormal and therefore free alpha Sasaki. So there's kind of a huge leap, right, from contact to free Sasaki, which is not the case if you're only looking at one such structure. I would have hoped I can escape that. So, well, this is one of the main. So for alpha Sasaki, okay, you definitely need d eta equals 2 alpha phi. And plus the Reb vector field psi is a killing vector field, plus another equation, which I will just skip. Okay?
You can say just a rescale free Sasaki.
Yeah, no, but she was just asking only free Sasaki, no, only alpha Sasaki, not free Sasaki. Was that the question? Yeah. So only Sasaki. Okay. Right.
It's the same.
No, but
Alpha Sasaki is a rescale Sasaki.
yes, I'm not claiming. Yeah, but that's okay. Well, that's another way of wording it. I mean, it's a rescaling of Sasaki. So why is it reasonable to look at alpha Sasaki instead of Sasaki? Well, because a constant multiple of a Sasaki metric is not Sasaki anymore. So actually, when you're working in the business, quite often it is more appropriate to look at alpha Sasaki right away because of this bad scaling property, right? So the transition from Sasaki to alpha Sasaki, there is not really anything going on. Okay, and when you do so, you pick up this factor, and Sasaki just corresponds to alpha equal to 1. Okay, good. Okay, so we're looking, the classical picture was to look at these three almost contact structures separately, and Kashiwara's theorem told you that whenever you are in this situation, then your manifold is automatically hypernormal and therefore free alpha Sasaki. Good. And now, what is the modification for free alpha delta Sasaki? So we look at an almost free contact metric manifold, okay, just as before. And now we add an additional term which is genuinely not there if you only look at one structure, right? Because we're requiring that d eta I is equal to 2 alpha phi I with the same constant alpha in all three situations plus twice alpha minus delta eta j wedge eta k, where the etas are the dual one forms of the Reb vector fields, remember? So this is the general condition, free alpha delta Sasaki is d eta I equals 2 alpha phi I plus 2 alpha minus delta eta j plus eta k, where ijk is any cyclic permutation of the indices 1, 2, 3. And we see immediately that alpha equal to delta, that's of course nonsense, is of a particular case because it makes the second term vanish, right? So we require alpha to be a non-vanishing real constant. Delta is allowed to be anything. And if alpha is equal to delta, we see immediately that eta I is 2 alpha phi I. And then we just recover the old notion of 3 alpha Sasaki manifolds. But in general, we require that there is a nice link between the geometry of the 2 free vector fields encoded in that equation. And it makes sense to distinguish 3 main classes of 3 alpha delta Sasaki manifolds. Namely, we call them positive if alpha times delta is positive. Right? And positive will be strongly linked to positive curvature properties. And therefore, alpha times delta positive, this is exactly the situation that we are interested in this talk. Negative corresponds to alpha times delta is negative. Okay? And there, for example, if we classify the homogeneous case and the positive case is basically what you suspect. It's all homogeneous manifold which you get as homogeneous vibrations over positive scalar over quaternionic Kähler manifolds of positive scalar curvature. But we know that if you are looking at quaternionic Kähler spaces of negative scalar curvature, then you get non-symmetric examples due to Alexevsky-Cortez. And I'm just mentioning that it is really possible to construct negative 3 alpha delta Sasaki manifolds by using these Alexevsky and Cortez spaces. So it gives you a nice way of using them for this kind of geometry. And the degenerate case is if delta is equal to 0. For example, you get here the quaternionic Heisenberg group. Those are locally submersions of hyperkähler manifolds. So it's not so surprising that they have a more complicated and challenging geometry. But there's a nice paper by Gerges, Roschig, and Stecker which says what you can expect in that situation as well. Okay. Good. So here comes a few theorems on 3 alpha delta Sasaki manifolds, but that's a topic on itself, so I will be extremely short on that. So the first thing is the structure is always hypernormal, and therefore we get kind of a generalization of Cauchy-Ward's theorem, which covered the case alpha equals delta equal 1. The distribution V is always integrable with totally geodesic leaves. The Reb vector fields are automatically killing vector fields, and they satisfy the commutator relation that psi I commutator psi j is equal to 2 delta psi k. And that gives you a geometric direct interpretation of the constant delta appearing. No, that's not working. Okay, you cannot point to the blackboard. So here, of this constant delta. And therefore, the vanishing of delta means exactly the degenerate case is when the 3 Reb vector fields commute, which obviously gives some nice, very different geometry. And of course, if delta is positive or negative, we see that we get SU2 locally or SU11 as a Lie algebra. Okay, the Levi-Civita connection, I mean, this is basically only just to show you that you can compute all these things, right? And you get alpha minus delta typically as a factor in many terms. In particular, this first equation is something we are used to from alpha Sasaki manifolds, right? The Levi-Civita derivative of phi in direction xy is given by this linear combination. And then you get similar terms, right, which basically come from permutations of the indices and the other almost complex structures phi j, phi k, which enter the picture. Okay, so these things can be computed, and we see how we get the additional terms from the phi alpha Sasaki case. And now there's a reason why I call these positive, negative, and degenerate 3 free alpha delta Sasaki manifolds because there's an easy homomorphic argument behind. So you can define as a basically straightforward generalization of tunnel deformations, which one uses in almost contact geometry, H homomorphic deformation, H in the sense of H in the horizontal space, right? We rescale the one forms, we rescale the Reb vector field with the inverse, we keep the almost complex structures phi I, and then one has to adapt the metric G by some rescaling in the vertical direction and another rescaling in the horizontal direction. And for all that to work out, the constants A, B, C appearing here have to satisfy some equations. So this is, again, a free almost contact structure if you started with one, but even better, if you started with a free alpha delta Sasaki structure, then it's going to be again a free alpha delta Sasaki structure. It's just that the values of alpha and delta changed, and you can compute them. So the new alpha is the old one rescaled with C over A, and the new delta is the old delta rescaled with 1 over C. In particular, we realize if delta vanished in your original manifold, then it's going to vanish whatever deformation you perform. So the class of degenerate free alpha delta Sasaki manifolds is closed under these deformations, clearly. And secondly, we see that the sign of alpha times delta is preserved as well, because C cancels out, and there's A left, but A is positive. So indeed, when I perform this deformation, I stay in the positive, negative, or degenerate class. And moreover, one sees easily, if I'm in the positive alpha delta case, this is the case even only if my manifold is homomorphic to a free alpha Sasaki manifold, alpha delta equals 1. And if alpha times delta is negative, it's homomorphic to 1, which doesn't have a classical name, but is kind of the analog, right? Alpha equal to -1 and delta equal to +1. So I can normalize the product to be 1 or -1, depending in which class I'm looking at. And now if you want to take it easy, you can say, okay, free alpha delta, that's just H homomorphic deformations of free Sasaki manifolds. That's true in a sense, but it makes your life much easier as far as computations and understanding the structures go. And in the negative and degenerate case, you get new geometries. Good. So here comes a short intermezzo. Some of you I have known for many years, and you know that one of my favorite subjects is metric connections with skewed torsion, right? And this form already points into that direction. So, very short intermezzo, metric connections with skewed torsion. Now, we've heard Robert Bryant's talk on holonomy this morning, and one crucial aspect of this wonderful concept of holonomy is that assuming you are in Berger's generic case of holonomy SON, then holonomy, Riemannian holonomy does not give you any information about the underlying geometric structures. But we know that the Berger's list is impressive but short, in the sense we have G2, we have spin 7, and so on. But if it's not one of these, if you're not dealing with a Joyce or Calabi-Yau manifold, maybe you would like to say something using ideas similar to holonomy nevertheless. And the way is to replace the Levi-Civita connection by a connection with torsion. Okay? So basically, whenever Riemannian holonomy does not give you enough information, then one way out is to find a metric connection which is adapted to the geometry. In particular, this applies to the whole world of almost contact geometry, because no contact manifolds appeared in Berger's list. Right? Which is, of course, because the structure group is never acting in an irreducible way, because it's un in dimension 2n plus 1, so you have a one-dimensional trivial copy, or trivial representation. Okay, so metric connection is said to have skewed torsion if the free form which I derive from the torsion tensor in the usual way is actually skew symmetric with respect to all indices. Good examples are, for example, the Ambrose-Singer connection. So we know from the Ambrose-Singer homogeneity theorem, a Riemannian manifold is homogeneous if and only if it admits a Riemannian connection. It's satisfying these two conditions. Curvature and torsion are parallel. And I would like you to see that as the generalization of Cartan's definition of symmetric spaces as being those with Levi-Civita parallel Riemannian curvature tensor. Right? So the torsion tensor T measures in some sense the difference between being symmetric or not symmetric. Okay. And moreover, this Ambrose-Singer connection actually has Q torsion if and only if my homogeneous space is what it is called to be naturally reductive. Okay. Connections with Q torsion, I think it's fair to say, are by now an established tool for the investigation of almost Hermitian manifolds, manifolds with G2 structures, Sasaki manifolds, and many others. When you are in the general picture of a G reduction, so G, a subgroup of the frame group, if we look at the frame bundle of your Riemannian manifold, right? Therefore, it is an S. You look at oriented. My manifolds are oriented by definition. So the group is S. Structure group is SON, and suppose you have a reduction of the frame bundle to a subgroup G, really different from SON. Okay, so for such a G reduction, then under relatively mild assumptions, one can prove that there's always a unique metric connection with skew torsion, which is based on a very nice holonomy theory for connections with skew torsion by Olmos and Reggiani. Okay, and whenever I have a connection with parallel torsion, I get for free certain objects. In particular, if the torsion is parallel, then the curvature operator of that metric connection with torsion is indeed a symmetric operator on two forms. And moreover, the differential dt is given in an algebraic way out of the torsion. So it's this quadratic expression. You take sum of a normal basis, EI, take the inner product with T, wedge it with itself, sum over your basis, and this is what I call sigma T. Now, there's a different definition from sigma T, which does not use an orthonormal basis, but that we don't need. You could say, okay, well, this sigma T, I mean, that's an expression. You can do that. Why would you? Well, of course, the first hint is that it gives you just the computation of dt, which in general is not going to be 0. But when you start working in the area, you realize that you cannot escape sigma T. Sigma T is going to appear whatever you do. For example, it will appear in curvature identities. It will appear in the Bianchi identities because the classical Bianchi identities now have correction terms, and sigma T measures these corrections. It is, in a well-defined sense, a measure for the non-degeneracy of T. For example, if you are on a nearly Kähler manifold, right, then you can take, then you have your most complex structure, omega. If it's 6-dimensional, star omega is going to be a 4-form, and this 4-form is just going to be the sigma T of the gray connection. Similarly, in dimension 7 for a nearly parallel G2 manifold, you get automatically the dual of the free form of the G2 form, right? So it's going to pop up, believe me. And so whenever you are dealing with a G structure which fits into that frame, namely you have a G reduction which assumes, or which in some good metric connection with skew torsion, then the form sigma T, which I'm introducing here, comes up in a natural way. And so let's write that up, right? So we have a connection nabla with torsion T in the free forms, and then dt is equal to 2 sigma T, which is the important 4-form to look at, of course, only if lambda t is 0. Okay, good.
So parallel T plus closed T. Parallel and closed
implies degenerate. For example, parallel plus closed means in the irreducible case that it is a Lie group. Right? That's a discussion we had at some moment. It's assuming that it's acting irreducibly.
So like we smooth flat. So
Yeah.
that would be.
Yeah. Right? Yeah. Okay. That's in our paper on the classification of nearly naturally reductive spaces in dimension smaller equal 6. Yes. Okay. So this is really a quantitative statement. Okay. Now, free contact geometry does not correspond in a one-to-one way to a reduction of the frame bundle, and therefore it does not fit immediately into our scheme. Nevertheless, things work out nicely because we prove that every phi alpha delta Sasaki manifold admits a unique metric connection with parallel skew torsion such that, well, this equation holds. So the derivative in direction x of phi I is a linear combination. It's not 0, but it's a linear combination of phi j and phi k. So basically, it should remind you of the behavior of quaternionic Kähler manifolds, right? But now the connection here is not the Levi-Civita, but my connection with skew torsion. So I don't have the three single structures, phi I are not parallel, but at least I have they span a parallel distribution. That's the best way to phrase it. And the constant beta, which appears here, can be computed, and beta is twice. And now this is surprising because maybe you would suspect delta minus alpha. I certainly did, but it's not. It's delta minus 2 alpha. So one of the messages here is that besides free Sasaki geometry, there's a second line of values of particular geometric interest, what we called parallel phi alpha delta Sasaki, just because it makes all these structure tensors parallel. Because if beta is equal to 0, right, delta equal to 2 alpha, so here is the alpha delta plane. The degenerate case would be that line. The phi alpha Sasaki corresponds to alpha equals delta, so that's that line. And now the red line is this new line of vanishing of the constant beta in that equation. Okay, good. And this connection is unique in a certain sense, and we call it the canonical connection of the free alpha delta Sasaki manifold. So the analogy to quaternionic Kähler I already described. If beta equals 0, then everything is parallel. And moreover, now you can get very explicit expressions. For example, the dt of that connection, right, which by what I wrote on the blackboard is of interest to us, is something you can control. It basically has a term which is just the horizontal parts. So, right, the far i's, I can deduce the non-horizontal part. So it's the wedge products of the horizontal parts plus an extra term which mixes the horizontal parts with some vertical component. So it's good to know exactly where on these distribution H and V things are living, and that's what that formula achieves. And we see in particular that we only get a horizontal contribution whenever we are in the situation of vanishing beta. Okay. Furthermore, I already said so, and now let's put that into a precise statement. Namely, based on the work by Clayton, Zimmerman, and Moriano, we can prove that these manifolds admit a very nice locally Riemannian submersion. Namely, every phi alpha delta Sasaki manifold is locally a Riemannian submersion over a quaternionic Kähler manifold, which I'm going to denote by N, with totally geodesic fibers, tangent to the vertical distribution, and the Levi-Civita connection on the quaternionic Kähler manifold is the projection of the canonical connection, the canonical connection I just described, upstairs. Right? There is a way to give the formulas explicitly and then to see how these things carry over. Right? So we get, philosophically speaking, basically all the same equation for the Levi-Civita connection on the base, but now with a factor of 2 delta. And there's a very easy formula for the scalar curvature of the base, namely it's a multiple of alpha times delta, which again shows us that the sign of alpha times delta, if it weren't for the properties under homothetic deformations, this would be clearly the moment where you notice that this is the distinction to make, right? Alpha delta, positive, negative, or vanishing. Good. Okay, so this submersion helps us in identifying things and in coming back to our problem of positive, strongly positive curvature. Okay, so here comes the naive approach, right? That was our original idea, as it usually is. Original ideas don't work, but they have a grain of truth in them. So let's consider with the Riemannian curvature operator as a symmetric operator on 2 forms. Furthermore, we have our connection, nabla, and we have its curvature operator, which is also symmetric on 2 forms because we know that we have vanishing, or that the torsion is parallel. Good. We have our submersion, and then with that submersion, we can express the curvature of the canonical connection upstairs in terms of the Riemannian curvature downstairs, plus an extra term, which depends on the horizontal part here. Okay? For all horizontal lifts, x, y, bar, of vector fields living on the base n. And actually, for example, we get a very nice formula, I just like it. So on the quaternionic Kähler base n, we see that the Riemannian curvature operator acting on the horizontal parts of the free ice, these are actually eigenforms. And finding eigenforms of curvature operators, right? I mean, I'm acting on 2 forms. He would like to decompose the space of 2 forms in a good way. So the best way is to find as many eigenforms as you can. It's a symmetric operator. It can be diagonalized, right? So that's one of the tedious parts, right? Finding curvature eigenforms, as many as you can. So here's one which you get for free on the base. And now, here's the relation between, so we would like to prove that our total space M, our free alpha delta Sasaki space, has strongly positive curvature or strongly non-negative curvature. When is that the case? And does it have anything to do with the 4 form induced by the canonical connection? So, first thing to do is to express curvature. And the Riemannian curvature of the manifold is equal to the curvature operator of the canonical connection plus 2 extra terms. The first extra term is this GT, which is basically turning the torsion tensor T into an operator, right? And this is easily seen to be non-negative. And furthermore, sigma T as a 4 form, of course, also induces a map on 2 forms, just as in the original idea of Thorpe, right? Which is exactly that contribution. And remember that this is just dt. So the naive idea is, suppose you can prove that the curvature operator of the canonical connection is strictly positive. Then the Riemannian curvature operator minus 1/4 sigma t would be equal to r nabla plus this term, which is non-negative anyway. And then we would be able to conclude that we have strongly positive curvature. Now that doesn't work out, but philosophically it's right. Okay, so in particular it means that the candidate for the 4 form is minus 1/4 sigma t. Good. Here comes the easy case. Easy in the sense, if you know all the things about curvature that I have been talking about, I didn't show you, then you can prove it. It's still not a one-liner, but it's the easier part of what I'm going to say from now on. So, easy. Suppose you have a homogeneous free alpha delta Sasaki manifold. First thing is, if alpha times delta is strictly negative and the base, the quaternionic Kähler base, is symmetric, then indeed the curvature operator is non-positive. Right? Symmetric, well, we need a lot of information. In the homogeneous case, we have more curvature information than in the Bush general case. That's why homogeneous is of importance here. And if alpha times delta is positive, then R is non-negative, and if and only alpha times beta is non-negative. So if you're interested not in strongly positive, but you are happy already with strongly non-negative curvature, here you get a whole zoo of examples quickly, right? And in particular, a positive homogeneous 3 alpha delta Sasaki manifold is strongly non-negative with 4 form minus 1 over 4 sigma t if and only alpha times beta is non-negative. Now, you remember my picture of this plane, right? And the line so this was my alpha delta plane. Here was the diagonal corresponding to 3 alpha Sasaki, right? And then there was this parallel case, which was delta corresponds to 2 alpha, and alpha times beta positive is anything which is here, which means in particular that this does not cover 3 homogeneous 3 alpha Sasaki manifolds because this condition just fails. So these basically one could not see in the old frame, I would say, of notions because this, well, we just didn't look at the whole plane. We only looked at that one line, right? And if you consider only that line, then you miss a few things, and this is one of the things one misses. Okay, so this is a first neat example. Now I said that one of the crucial parts is to find eigenforms. So there's not going to be a test on that after the talk, right? But just take home message, there are a lot of eigenforms, and that's a little bit how they look. So for example, the curvature operator of the canonical connection has 6 orthogonal eigenforms of the form phi I minus phi jk, psi jk, which of course means the wedge product of j and k, right? And here is the eigenvalue. Then we have other linear combinations which have 0 eigenvalue. And then you would like to control the signs of these eigenforms, right? And for the Riemannian curvature operator, the following are equivalent, which is kind of funny, namely, so the last one is, it is Einstein. And from the curvature information I didn't show you, we know exactly when a 3 alpha delta Sasaki manifold is Einstein. There are exactly 2 situations, namely either alpha is equal to delta, which is just the alpha Sasaki case, and we knew that these were Einstein, or delta is equal to 2n plus 3 times alpha. Okay, so the Einstein case is well understood, but what's funny is that the Einstein condition can be rephrased in terms of eigenforms of curvature operators. So, namely, it's equivalent to saying that each of the forms phi I minus psi jk is an eigenform of the Riemannian curvature operator, or equivalently, each of the 2 forms, which I wrote down here, is an eigenform of the Riemannian curvature operator. And if we are in the 3 alpha Sasaki case, then that's all nice, because then we have 6 eigenforms with the same eigenvalue, which is just alpha squared. Okay, so if you need contact manifolds with many eigenforms for curvature operators, I recommend using these. All these computations will then be good to recycle. Okay, and here comes the main result. So, suppose you have a 3 alpha delta Sasaki manifold, canonical submersion pi to the quaternionic Kähler base as before, and assume that the base has strongly positive curvature with respect to some 4 form omega, right? And suppose that this 4 form omega acts on the distribution spanned by the 3 almost complex structures with minimal eigenvalue nu. So it may have larger eigenvalues, but nu should be the smallest one. And the claim is, if the quotient delta over alpha is sufficiently large, so I'm saying this is a condition, I can write it down in an equation. The equation doesn't tell you anything, but if you look at the equation and coefficients, you realize you can always achieve that it is sufficiently large, so there are solutions. So if you choose them sufficiently large, then the manifold upstairs M is strongly positive, and the four-form is the pullback of the omega of the base minus 1 over 4 sigma t plus a slight addition, some epsilon entering the picture, right? And epsilon strictly positive, of course. Good. So you can do a slight modification of the naive approach which I had explained at the beginning. And the corollary, which still takes a bit of time, is that the 7-dimensional 3 alpha delta Sasaki manifolds with positive sectional curvature admit, indeed, H-homothetic deformations with strongly positive curvature. Okay, so you can deform positive sectional curvature into strongly positive curvature, which we knew is a stronger condition. Okay, and the corollary in particular is that the 3 alpha delta Sasaki spaces, which appeared in the work of Betziol and Mendes without saying what the four-form is, now you can apply that, because in that situation we know what the quaternionic Kähler base is. We can tackle the omega and we compute the nu, which is in this general theorem. So indeed, for the Wallach space, you get minus 1 over 4 epsilon sigma tau for small epsilon, and for quaternionic spheres and for quaternionic real projective spaces, you can also do things, and then you see here the p star omega, basically in the first case, wasn't there, whereas you realize that here you get something, which is that contribution, and these are strongly positive even only if alpha times beta is strictly positive. So this is the quantitative version of the Betziol-Mendes theorem, and it shows us, yes, indeed, all the information is encoded in sigma t, maybe not in the straightforward way because of the little epsilon, but basically the geometry coming from the canonical connection encodes the property of strongly positive curvature. Right, and okay, here comes the sketch of the proof. I have 2 minutes, 3 minutes?
Well, 1 minute.
Yeah, 1 minute. Okay, so, but we started 5 past. Okay, good. So, what do? Well, you look at all curvature operators in detail. In particular, you split the curvature operator in what would be the curvature operator for parallel case, beta equal to 0, plus a second term. Compute everything. Compute the spectrum. You get certain eigenvalues, which, of course, uses all this information on eigenforms. Right? You get some intermediate result then with for alpha beta non-negative, and I switched to, so you identify all terms, you get certain stuff, and in particular you have to decompose a space of 2 forms in certain summands, 2 forms with purely horizontal term, with 2 forms with purely vertical terms, and h times v, and then you get certain summands, and then you deal with all curvature summands on all these pieces, and put it all together in the right way to get the result. And I guess that's it. Thank you very much.